Hello, Aspect. I am Xuewu Zhang, the presenter. I am from Sichuan University, China. The article I presented is titled Fatigue Damage Mechanism in Hygrothermally Aged CFRP, based on in situ DIC observation and SEM characterization. I mainly present from the above six aspects. First, research background. Carbon fiber reinforced polymer composites are widely used in aerospace, automotive, rail transit, and other fields due to their excellent mechanical properties and lightweight potential. Laminated plates constituted its main structure. The focus of this study lies in the fatigue life and mechanical properties of CFRP laminated plates under complex environments such as depth and hot conditions. Next comes the experimental part, starting with experimental preparation. This project primarily utilized DIC technology and SEM technology to investigate the fatigue life and mechanical properties of CFRP limiters from two perspectives before and after hygrothermal aging. The laminated panel specimens were fabricated using T3003K carbon fiber and T300EM119 resin based composite materials through an autoclave molding process. To simulate the depth heat aging scenario, this project conducted a depth heat aging test. The test was conducted in a water bath environment at 8 degrees Celsius, and the test pieces were weighted at corresponding intervals when the moisture absorption rate was less than 0.02%. It was considered to have reached the moisture absorption saturation. Static tests were conducted using the MTS800 tension torsional composed testing machine, and the results of these tests served as the basis for fatigue tests. The fatigue tests were conducted at 5 different strength levels until the specimens fractured. It was considered that the specimens would not fracture when the number of circles exceeded 1 million. This is stress loading level for fatigue testing. It takes approximately 804 hours for the test specimen to reach moisture absorption saturation. The moisture absorption rate of the 45-degree laminated board is lower than that of the 90-degree laminated board, as can be seen from the figure. The moisture absorption of the test specimen mainly consists of 3 processes: linear region, diffusion zone, and saturation zone. Due to the high dispersion of fatigue life exhibited by composite materials, this study explores probabilities, design, and reliability methods for evaluation. Using the basic model for fatigue life prediction, the red SN curve indicates that after depth heat aging, the 45-degree limited exhibits a higher fatigue life under the same limited load radio. However, the fatigue life of 90-degree laminated boards is relatively low. This is mainly due to depth heat aging, which causes the ultimate load of 45-degree laminated boards to decrease by approximately 154%. The DIC technology was exploited for analyzing the full-field strain distribution and evaluation. For the DIC image of the 45-degree laminated plate, it is evident that the strain of the specimen exhibits an approximate periodical circle, which is related to the loading of fatigue stress. The damage propagates from the internal towards the 45-degree direction, determined by the fiber angle. The test piece after depth heat aging will be poured longer, because depth heat aging makes the fiber more ductile. For 90-degree laminated boards, it can be observed that damage begins at the edges and extends inward. This is due to fiber debonding caused by depth heat aging, resulting in uneven stress distribution. Additionally, the strength of depth heat aged 80-degree laminated boards is less than that of 45-degree laminated boards. The reduction of dynamic modulus or stiffness is currently a widely used method for assessing the degree of damage in continuous fiber reinforced composites. In this study, a general fatigue damage model based on the fatigue mechanism of composites was employed for stiffness prediction. As shown in the right figure, they are respectively the relative degradation rate chart and the cumulative stiffness damage chart. After depth heat aging, the cumulative stiffness damage rate of the 45-degree test specimens decreases. It is also evidence that the relative degradation rate of the 45-degree test specimens after depth heat aging becomes slower. The depth heat aging test results in a rapid increases in the rate of stiffness damage. Accumulation in laminated place with a 90-degree layup angle during fatigue testing. This study utilized DIC technology and SEM for fracture characterization. The fracture images clearly reveal that the 45-degree laminated board after depth heat aging becomes more elongated, and the fracture surface presents a 45-degree angle, primarily due to the fiber orientation at a 45-degree angle. The fracture surface of the 90-degree laminated board after depth heat aging transforms from a neat straight cut to an angular shape, mainly because depth heat aging causes the fibers to no longer adhere together, leading to uneven stress distribution on the fibers. Finally, conclusion. Through systematic experiments and rigorous analysis, I have found that based on after depth heat aging, the lifespan of the 45-degree laminated board is significantly enhanced, while the fatigue life of the 90-degree laminated board is severely reduced. The damage of the 45-degree laminated board extends from the middle to both ends, while the damage of the 90-degree laminated board starts from the edge, and the overall strain is relatively small. The stiffness of 45-degree laminated board decreases due to aging, but the degradation rate slows down. The SEM fracture surface rewards that 45-degree laminated board primarily exhibit delamination and interfacial failure. 90-degree laminated boards mainly show fiber fracture and debonding, with aging affecting the fracture morphologically. Okay, my presentation ends here. Thank you.